Yeah, so maybe I can start to those who don't know our today speaker yet. We are happy to welcome Wolfgang Spohn and Mantas Radzvilas, who are new to the collective behavior cluster. They got affiliated recently, but they are not new to the university. So but in any case, we're very happy to have them with us today and present on a topic that is not as common in our seminar as all the biology and topics on critters and other collective phenomena. So today it will more from the science philosophical view, as I understand. So then we can start.
Okay.
And welcome Wolfgang Spohn.
For the kind introduction. We are very grateful, Mantas and me are very grateful that we can present our ideas as newly or recently associated members of your cluster. It's a joint talk, that is, we have produced it jointly, but then we decided that it's only me who will present this, because we find that always a bit odd with these alternating speakers back and forth. So it's just me who is presenting that. But as I said, it's a joint presentation. And the presentation is about game theory, which is well known to be foundational for micro and for macro economics, and it is also important for the social and for the political sciences, and even for biology, namely for the evolutionary biology part, which also uses game theoretic methods quite a lot. And we will present results from the game theoretic part of my Reinhard Koselleck project on reflexive decision and game theory, which started in October 2020 and will last till September 2025. I'm not going to explain what the reflexive really refers to. Yeah? That would be a longer story. So the presentation will consist of 4 parts. So first about motivation, which will be about social norms, and where the focus is that the standard equilibrium concept of game theory, the concept of Nash equilibria, is not well suited to capture the idea of social norms. And I exemplify that with a few examples. Yeah? And that should motivate our novel equilibrium notion, which we call dependency equilibria, and that will be formally explained in section 2. And then we will return to the examples. What are the dependency equilibria in the examples? And finally, I will be talking about evolutionary dynamics, which may be able to explain these equilibria. So these are the 4 parts, and that's 26 slides altogether, and then we are through. Okay, so we may start with phenomena of coordination and cooperation, which are, of course, very salient and ubiquitous in human society. Yeah? We have that all the time. You will know better than me to the extent to which they may be also found in the animal kingdom, in animal groups. Now, game theory, if you look at it, has surprisingly hard time with explaining these phenomena of coordination and cooperation, and needs surprisingly big efforts to overcome them. Yeah, it's a long story what they do, and I won't tell that. I only state the difficulties game theory has are really quite surprising. For instance, look at the paradigmatic poor coordination game, CG, and I guess you know how to read these matrices. So player 1 has 2 choices up and down, player 2 has 2 choices left and right, and the figures then they do each player does something, chooses an action, and the outcome is determined by both of their actions, or as I say, by an action profile. And then the players evaluate these outcomes according to their interests, and these are these figures. The first figure is the utility of player 1, and the second figure is the utility of player 2. So in that game, pure coordination game, the only interest is they have that they meet on the diagonal somewhere, yeah? But it doesn't matter where, yeah? this is as fine as this one. But that would be bad, and that would also be bad. So that's the pure coordination game. Yeah? Now, the core assumption of game theory, since it exists, almost since it exists, since 1951, in so-called best response reasoning, each player chooses such that, given the choice of the other player, she cannot improve by choosing differently. That is, the players play a Nash equilibrium. That's the defining characteristic of a Nash equilibrium. And the coordination game has three such equilibria. One is up and left, and the other is down and right. These are the pure Nash equilibria. And then there's also a mixed Nash equilibrium, where each one chooses his strategy with probability 1/2. That's also an equilibrium. Yeah? No one can do better than so. Given that you randomize, so to speak, the half-half with left and right, then I can't do better than by choosing either up or choosing down or mixing it as well. Okay, and the other way around. So you know the notation for the rest of our talk. Yeah? Now, social scientists tend to say that such coordination problems, which are ubiquitous as mentioned, are solved through social norms or conventions governing human society. Yeah? And what exactly is a norm? Yeah? And vaguely one can characterize them first by their arbitrariness. Yeah? It's important that some norm is established, but exactly which one doesn't really matter, as in the coordination game. And it's also important that there's some internal stabilization mechanism. So it's not the external forces who are responsible for the stability of the norm, but somehow an internal mechanism. And I don't know, but again, you will know better, that there are maybe animal groups which are governed by norms in this sense. Now, which norm gets established is usually a matter of historical accident. However, there are good explanations of the stability of norms, just as game theory can well explain the stability of Nash equilibria, precisely by the fact that no player has an incentive to deviate from the Nash equilibrium. But still, there's a subtle difference already in the coordination game case. In the first Nash equilibrium of that game, you do left and I do up. And we both believe this, whereas we would describe a norm as governed by a reciprocal dependence and mutual conditional expectation. I do up if and only if you do left, and I do down if and only if you do R. And that's not written in into the Nash equilibrium. So that becomes clearer in the next examples. Another paradigmatic game is the so-called stack hunt, which is not only about coordination, but also about cooperation. Yeah? And the idea is you and I go hunting. Yeah? And either we go hunting hares, each by oneself, or we join in hunting a stag. Yeah? You need two people to hunt a stag. Yeah? So that's the stag hunting. Yeah? Up and left are stag hunting, and then and that's the best thing we can do. Yeah? If we both hunt hares, well, then a hare is not so delicious as a stag. But then, of course, maybe I go hunting. I go for a stag, and you go for a hare. Then I'm left with nothing, yeah, because I won't be successful, yeah. And you have an easier time to do the hare hunting because we don't compete for hares, yeah? So you have better chances to get the hare, yeah. So that explains the utility of the stag hunt. And again, there are three Nash equilibria. We can cooperate and go for the stag, or we can not cooperate and both go for hares, and again there's a mixed equilibrium. And again, game theory can't predict which Nash equilibrium is reached. It can only say that the cooperative Nash equilibrium would be more desirable. By contrast, we would expect that a norm in favor of cooperation would be established. So there's already a slight difference. And the point is even more salient in another paradigmatic game, which is about domination and submission, or peace and war, even more dramatically. It's called hawk and dove in the game theoretic literature, also chicken. Yeah? Chicken in the sense of Feigling, nicht chicken in the sense of the animal. And there the thing is, here the up and left are the doves, and the down and the right are the hawks. And now we might be peaceful, both two doves, and that's in a way the best for. It's not the best for both. Oh, in one sense, it's the best for both. But of course, if you are a dove, then I would prefer to be a hawk, because I dominate you and have a still nicer life. But on the other hand, and the other way around here, and of course, but if two hawks meet, then they fight each other, and that's the worst outcome for all of them. So the question is, do we go there or do we go there? And again, we have pure Nash equilibria, this one, that hawk, that hawk and that dove, or that hawk and that dove, that's here. Or finally, there's a mixed Nash equilibrium again. And of course, what the mixtures here really are, that then crucially depends on the specific numbers and the utilities. And I've chosen that easily, so that it's always this one, the Nash equilibrium. Okay. And finally, of course, the most famous game of all, the prisoner's dilemma, which is also about cooperation. But there it's more dramatic than in the stag hunt, because, so that's the utility table. You can, if we cooperate, we both get 2. If we defect, that's D and R, we both get 1. But if I defect and you try to cooperate, then you get nothing and I get even 3 units, and vice versa. And if you look at the table, as I say here, the situation is worse. Cooperation is dominated by defection. That is, whatever you do, I'm better off by defecting. If you cooperate, then I get 3 instead of 2, and if you defect, then also I get 1 instead of 0. So, of course, somehow we would like the two people to cooperate. They are better off together, if they cooperate. But it seems that there's no way to get them to cooperate, at least in the single-shot game of the prisoner's dilemma. And that has many variations. That game, in a multi-person setting, this game is called the tragedy of commons. For instance, as exemplified in the so-called voting paradox. Why should we go voting? That my vote makes any difference to the result of the elections. It's so very unlikely, that one vote. So it doesn't, it's not worth the trouble going to the election office and so on. But if everyone has that attitude, no one goes voting, and no one would desire that. And that has, again, many variations. Or the free rider problem is another important example. So, and again, we would expect that in such cases a norm will be established that enforces or at least favors cooperation. But I didn't, so the only Nash equilibrium is joint defection, and as I said, the situation is worse. We need not appeal to the equilibrium consideration, we can appeal only to the dominance argument. So at least the last 2 examples show a discrepancy between Nash equilibria and social norms. There are many ways to reduce the discrepancy. The 2 most prominent are, namely, first, to sanction deviations from the norm, that is, to punish hawks and defectors. Thereby we change the utility functions, and cooperation and peace without domination become Nash equilibria. But the point is, then we are no we are no longer discussing the original games. Yeah? We are discussing different games which weren't problems at all. Yeah? So in a way, we avoid the topic, so to speak, by that solution. Yeah? And another much more complicated way is to study the repeated play of games, in the hope that we see a norm involving them. So the idea is not that there's just one play, single shot play of the game, but rather we imagine that we are continuously engaged in these kinds of games, possibly in infinite series, but that's already a big idealization. And then the equilibrium, the equilibria are distributed in an entirely different way. But that involves a very complicated part of game theory, namely the theory of repeated games. But then that is also a kind of maybe an explanation of the desired behavior, that is, of the evolution of social norms. Here we want to propose another move, namely to take seriously the mutuality of expectations as established by norms. So if in the prisoner's dilemma I'm confident that you cooperate if and only if I cooperate, then joint cooperation is very likely given I cooperate, and joint defection is very likely if I defect. And thus I maximize conditional expected utility by cooperating, clearly. If your cooperation is very likely when I cooperate, and your defection is very likely when I defect, then the conditional expected utility of cooperating is greater than that of defecting. Yeah? The point then is that the choices of the other players are now taken as so-called act-dependent states of the world. Yeah? So what you do depends on what I do. Yeah? So your action is in a way a state of the world for me, but a dependent one, yeah? Dependent on my action. And in that case, rationality would require maximizing conditional expected utility. Yeah? Okay. So that was the motivation. So then I can explain what our novel notion here is. So again, let's just assume the very simple case, two players, 1 and 2, with choice sets A1 and A2 of actions or pure strategies, as they are called. Their choices result in an action profile A, consisting of A1 and A2. And if for player I, AI is the choice of player I in the profile A, then A without I, that's how I read that, A without I is denote the choice of the other player. That's a convenient notation. Then we assume that each player has a utility function, U sub I, from the action profiles into the set of real numbers. And that's already all we need to define a game. A game as in normal form, as they call it. So a game in normal form is made up by the set of players, their choice sets, and their utility functions. So that's very simple. Now let delta of AI be the set of probability distributions over the choice set AI, and delta A the set of distributions over the set of action profiles. And there are various interpretations to these probabilities, and that's a long topic as well. I just mentioned the three interpretations of the probabilities. Such a distribution, PI, may be interpreted first as a mixed strategy of player I. So I'm actively mixing my various pure strategies, throw a die or whatever. So that's one interpretation as a mixed strategy. But of course, a mixture of my actions can also interpret it as a belief of yours. Yeah? You have some beliefs about me, that is a probability distribution over my actions. So that's the second interpretation. And in an evolutionary context, the interpretation is an entirely different one, namely as a population share. Yeah? And then so each strategy is sort of realized in a population of a certain kind, yeah? And then a population may be more or less successful. Yeah? And yeah. Okay, and we come to that interpretation as well later on. And then a joint distribution, P over the strategy profiles, may be a dependent, or maybe an independent product of the two individual distributions over the choice sets of the individual players. And this will be the case when the PI are taken as mixed strategies of the players, or when the players have beliefs about the other one independent of their own choices. However, a joint distribution P may also be display dependencies between the choice sets A1 and A2 and not decompose into independent parts. And that's what we will use now in the central definition. A Nash equilibrium, as I have already indicated, assumes the independent case. So the P, which is the product of P1 and P2, is a Nash equilibrium for the game considered if and only if for each player and each action BI of player I, the following holds, namely that that's the expected utility in the equilibrium, which can be also written this way, because the P of A decomposes in that and that in the blue parts. So that's the expected utility in the equilibrium. And now player I might consider, instead of playing his equilibrium strategy, to play some other strategy or action BI. And then, so that's the expected utility of the strategy BI, but that must not be larger than the expected utility in the equilibrium. So given the choice P without I of the other player, each player cannot improve upon her mixed strategy PI by changing to another choice BI. Or in the other interpretation, given I's belief P without I about the other player, any choice AI with positive probability maximizes her expected utility, and no other choice BI does better. So that's the standard Nash equilibrium since over 70 years. But now a dependency equilibrium removes the independence assumption. So we now take any kind of probability measure over the set of action profiles. And they form a dependency equilibrium if and only if for each player I and each action BI of player I, we have the following equation. Again, that's the expected utility of in the dependency equilibrium, which now may be written in this way. So the PA can be replaced by PI A without A given AI times P of AI. So that's just the definition of conditional probability, that we also, that results in that probability. And that must be larger or equal to the conditional expected utility of some other choice of mine, or of player I. So if I take, that's the conditional expected utility of that action BI, and then that must be smaller or at most equal than the other one. So the only difference here between the Nash equilibria and the dependency equilibria is what is here in magenta. So here I'm considering the conditional probability, and Nash equilibria are considering the unconditional probability. And I'm necessitated to consider the conditional probability because I have that dependent distribution, in which case rationality is about maximizing conditional expected utility. You may think, oh, is that always defined? And maybe it's not always defined. In that joint distribution, the strategy BI may have probability 0, and then that conditional probability is not defined. That's a flaw of the definition, but that flaw can be healed. But that's again more mathematics and so simply note it can be healed in a satisfactory way, and we need not longer worry about that issue. Okay. So that's just a different notion I propose. But then the objection which is I have heard, or we have heard most often, is that these strange dependency equilibria, they are sort of magical thinking, so my choice mysteriously influences your choice, as it were. Although non-cooperative game theory, and that's about that foundational part of game theory, the talk, non-cooperative game theory is built upon the explicit assumption of the causal independence of the choices of the players. So the players have to choose independently, and independently means causal independence here. But I'm apparent by looking at these joint probability distribution, where we have that dependence in the distribution, I seem to deny that, or to deny the presuppositions of non-cooperative game theory. Well, a notion I have not explained is that of correlated equilibria, and that's also already a notion which also allows dependence between the action profiles of the players. So I should extend the comparison also to the correlated equilibria. That would go too far to explain all that. But the point is, in the correlated equilibrium, we have a very natural explanation of the dependence, and therefore that's the accepted notion of dependence in game theory. So, and the game theorists usually think now we have successfully dealt with the dependency phenomena. But dependency equilibria have an equally, or I think equally natural explanation of the correlations. It's not magical thinking or not a mystery. Namely, dependency and equilibria so far allow only a probabilistic dependence between the player's actions, which does not entail a causal independence. That's the crucial point. Two items not causally influencing one another may be probabilistic correlated due to having a common cause. That's the standard explanation of probabilistic correlation. It's even a famous principle associated with the philosopher Hans Reichenbach, the so-called common cause principle. Each probabilistic correlation is either causal by itself or must have, here's the correlation, must have a common cause. So the dependency equilibria do stick to the causal independence of the player's actions, but take account of the fact that they may have a common cause. Now, what might be the common cause? That's of course now the mystery, or the question at least. Well, in my view, it is the player's mindsets themselves that cause their action. Your mental constitution causes your actions. And these mindsets may be causally and also probabilistically entangled, and thus entail a probabilistic dependence between their actions. For instance, a social norm typically brings about such a causal entanglement of their mindsets. That brings about these mutual expectations we have about each other. And also mutual expectations about the mutual mindsets. Okay, so so that would be in the explanation of how the probabilistic dependence in dependency equilibria may come about. And in a dependency equilibrium, this dependence is a stable one. No player has an incentive to deviate. Another consideration, which applies at least to the case of roughly symmetric games, is one given in terms of so-called self-similarity considerations. If we know that we are alike, we may expect to behave similarly, and this amounts to having entangled beliefs without the help of social norms. And regarding animals, it is presumably not appropriate to talk of sophisticated mutual expectations. It's difficult to impute them to the animals. However, self-similarity may be directly brought about there by the common genes. And so maybe that's built into the animals. As I said, I have no idea, but you may have perhaps ideas of examples where that may be realized in the animal kingdom. So that may make the point, the dependency equilibria interesting for the evolutionary biologists. So Now we can look at the examples again. What changes by looking at the dependency equilibria? The more important task of norms, we said, is to solve coordination problems as paradigmatically posed in the pure coordination game. In the pure Nash equilibria of that game, players' choices appear probabilistically independent. Yeah? So just this combination has probability 1. And so this B up is independent of left and right and so on. Yeah? So probability 1 events are always probabilistically independent of all other events. Okay, and if we would look at the correlated equilibria, we would find that all mixtures of the two pure Nash equilibria, which are given here below, are also correlated equilibria. They express a maximal dependence of the choices, these mixtures, and I would expect that this maximal dependence is preserved in the limiting mixture of a pure Nash equilibrium. Yeah? But in standard probability theory, it is not preserved. It rather changes into to independence. But because of that, the correlated equilibria have been argued to serve as an explication of social norms. But I would point out that in that game, mixtures of the two pure Nash equilibria are also dependency equilibria. Yeah? So that very argument may count or counts in favor of dependency equilibria just as well. The hawk and dove is perhaps more interesting. Yeah? We said there are asymmetric pure Nash equilibria, yeah? One hawk and one dove. Yeah? In the counter diagonal. Yeah? And there was a mixed Nash equilibrium, each playing with probability 1/2, one or the other strategy. And in that case, the expected utility of each player is 2. Yeah? And one argument for the correlated equilibria was that the optimal symmetric correlated equilibrium gives each player a higher expected utility, namely of 2.6 period. Yeah? So by engaging in the correlated equilibrium, the players can improve. Yeah? And this was taken as an argument for the usefulness of that notion. Yeah? Again, the two pure Nash equilibria are also dependency equilibria, because Nash equilibria are always dependency equilibria. But there's also a continuum of symmetric dependency equilibria, which reach out till the peaceful coexistence of up and left, that is of two doves, where each of them has a conditional expected utility of 3. So that's still better and still a stable equilibrium. In general, we can observe that each Pareto optimal outcome can be reached by a dependency equilibrium. Yeah? So that means that there are a lot of dependency equilibria, and there's a big problem about equilibrium selection, but we have that problem also with Nash equilibria, perhaps not so big, but still, so with dependency equilibria it's perhaps bigger, but it's also very different, just because of that claim here. Yeah? And we should also note that there are unhappy dependencies. Yeah? For instance, that would be where it's very likely that you have two hawks. That would be in equilibrium as well in that case. Yeah? And finally, the prisoner's dilemma. Again, there are two families of dependency equilibria. Oh yeah, what I wanted to explain in the slide I have left over, or I've left out now, that was that the calculation of dependency can be quite complicated. Already in these 2x2 games, you get involved into quadratic equations, and so already then the things become messy. On the other hand, the computation of Nash equilibria in general is also a very messy business. It's really equivalent to solving arbitrary polynomial equation systems, which gives a very hard time to mathematicians. So the two-person games are, as it were, the Nash equilibria in two-person games, they are a kind of computational exception. And insofar also a deception. So the point is, joint cooperation is a dependency equilibrium in the prisoner's dilemma. And that was the point why I first came to think of that notion at all. And that was about 20 years ago. Okay. So finally, evolutionary dynamics. So far, we have argued that such dependent or entangled beliefs should be allowed as describing the momentary epistemic state of the players. And we have argued that such entangled beliefs should rationally form a dependency equilibrium. And this is simply a consequence of the best response reasoning so familiar in game theory, where a best response now consists in maximizing conditional expected utility given the entangled beliefs. Of course, such dependent beliefs do not fall from the sky, and we should be able to tell stories about how they might evolve, and thereby we enter the large field of evolutionary dynamics. Originally, the idea of the evolutionary dynamics was that one standard justification of Nash equilibria, that was epistemically very demanding, working with rich so-called common knowledge assumptions, and it was very doubtful whether that common knowledge in that sense really exists. But then there seemed to be much cheaper evolutionary explanations of the evolution of Nash equilibria, namely somehow we assume a process, the dynamic process, and then under weak assumptions we observe that they converge to a Nash equilibrium. So that's how a Nash equilibrium evolves. So that would, and that is a favored explanation of Nash equilibria, and in particular, as I said, also applicable in so-called evolutionary game theory, where we do just precisely this. And these processes, now again, they have the threefold interpretation. They can be processes of repeated play among human players. They can be processes of biological selection for the more successful strategy. Or they may be merely in the head of one player, that is deliberational processes within the mind of one player. And that was an interpretation proposed by Brian Skirms 25 years ago. There are various families of such dynamics, and their common feature is that they gradually favor the strategies that are better or more successful at each given stage of the process. So people follow their strategies, and then they are more or less successful, and then another strategy would have been more successful in that constellation. So in the next play, that the more successful strategies get a higher weight or a higher probability for realization. And so, and then a subfamily is the family of best response dynamics, as it is called, and they only favor the strategies that are optimal at the given stage of the process. So there are different ways. You can say also the better, the more it profits, or you can say only the best one, the optimum profits, and all the other ones decrease their probability accordingly. The various dynamics behave similarly, but there are also significant differences. Their behavior is complicated. They may diverge or run in circles, but when they converge, they must converge to a Nash equilibrium. And then, since then, people study the conditions of convergence, and that can be, again, mathematically be very complicated. And the best thing is to do computer simulations. There you see what is going on. And I'm grateful to Mantas because he has done that for our case as well. One question then was whether there are plausible processes that converge to dependency equilibria instead of Nash equilibria. And the answer is yes, and I will give you just one example. Namely, the oldest and simplest examples or learning process is called fictitious play, and was invented by Brown and Robinson in 1953. In the two-player case, it works very simple. For a given game is played repeatedly. Each player records the statistics of her opponent's choices in the past plays, and takes the observed frequencies of those choices as the probabilities of the choices in the next play. Yeah? On this basis, she maximizes expected utility. Yeah? And each of the two players does that. Yeah? So I take a statistics of your behavior, and you take a statistics of my behavior, and we project these statistics into the future and maximize expected utility. And we can start this process from 0, or we might slightly generalize it by assuming arbitrary starting weights of the strategies. Yeah? So not from 0, but they have some initial weights already. Yeah? Good. So perhaps I don't need more formal notation. It's perhaps I think I already explained that very well. Yeah. So I call that the traditional fictitious play. Yeah? And that works like so. At each stage, it's play n. Yeah. You project the observed relative frequency plus the weights, modified by the initial weights of the strategies, and then you calculate the expected utility, in that case of up. And if that's larger than the expected utility of down, then you choose up, or player 1 chooses up in the n plus first play, and the absolute frequency of up go up by 1. And the absolute frequency of down stays the same. Yeah? Likewise, if down is better than up, and likewise for player 2. So that's the process. Yeah? And because best responses and only they increase their weight in fictitious play in that process, that fictitious play belongs to the family of best response dynamics. Yeah? And for two-person zero-sum games, fictitious play converges to the essentially unique Nash equilibrium. And for two-person 2x2 games, it also converges to some pure Nash equilibrium. I have forgotten to say that we should also make provisions for a tiebreaker, yeah? But that's all. If the two, if up and down are equal in expected utility, yeah? Then we need a tiebreaker, but that's also a technicality. Yeah? Okay, so for two-person 2x2 games, fictitious play converges to a pure Nash equilibrium. And when more strategies or more players are involved, then things may become very complicated in these dynamics. Now my proposal is to modify that a bit. There seems to be a partial blindness in recording only the statistics of the opponent's choices. A full statistic would observe the frequencies of all strategy profiles. And as in fictitious play, the players may project these joint statistics into the future. Yeah? For instance, you have done left in 90% of the cases where I've done up, but only 60% of the cases where I've done down. And hence, in the next game, your doing L is 90% likely if I do up, and only 60% likely if I do down. And on the basis of this statistics, I maximize conditional expected utility. Yeah? And I've written down that again, yeah, and how that moves. But it's already clear. Yeah? So I base my predictions about you on the joint statistics, and which seems to be a fuller statistical picture than if I take, as when I take only a statistic of your behavior and leave my behavior out of the picture. And that joint fictitious play, as I call it, is again a form of a best response dynamics, insofar as it only favors strategies which are best responses, in the sense of maximizing conditional expected utility. However, joint fictitious play does not so independently for the optimal strategies of the players. It only favors optimal strategy profiles. So basing future behavior on such a joint statistic looks at least as reasonable as the traditional fictitious play. And so let's look at some examples how that behaves. Now we have slightly modified that because that's the only game we have computed is the high-low. That's like the pure coordination game, with the exception that one meeting point is, so to speak, better than the other meeting point. Yeah? And there we have the observation, well, For instance, if we start in this way for a Nash equilibrium in the original fictitious play, that converges to the worst meeting point. But if we build in a slight dependence, as it is here, then even if the joint meeting point has a higher probability initially, we see the process converging here, this one. So the better meeting point converges to probability 1. And similarly in Hawk and Dove, that's also quite surprising. Yeah? As soon as we build in a slight asymmetry, as in that picture or in that picture, the dynamics moves this way for the joint piece of 2 doves, and all the other combinations converge to probability 0. Perhaps I leave out the stack hunt, but that's the same. So let's say this, we have found that the basin of attraction for the cooperative solution of the stack hunt is larger than in joint fictitious play than in the traditional fictitious play. Yeah? So that would be a distribution which already moves to the uncooperative solution in the stack hunt according to traditional fictitious play, but it still moves here to the cooperative solution in the joint fictitious play. And finally, the prisoner's dilemma, and then I'm done. As soon as, if there's a slight, no, it's not even an asymmetry, yeah, but look at that distribution, which is perfectly symmetric, which has just a slightly favors the diagonal, yeah, and disfavors the counter diagonal. In that case, it also converges to joint cooperation, yeah? That kind of dynamics. That is, the point is, if that's a reasonable dynamics, that joint fictitious play, and we have generalized that, we have to do more work about the behavior of these things. So far we have just these nice examples which shows that there really is a difference. It's not just the same as for in the traditional dynamics considered. It really behaves differently. But a systematic study is mathematically quite involved, but I find the examples quite impressive. So there's a point, and if that's acceptable, then we also have a good explanation how these dependent beliefs, entangled belief system may come about, and why dependency equilibria may establish and why they are reasonable. Okay, thank you very much. Now I've really talked long enough, I fear, yeah. Too long probably, yeah. Thank you.
For this really interesting talk. Are there any questions?
I've lined lots of questions.
Sure.
Go ahead.
I'm sorry if they're really stupid questions. So my understanding is that the dependency equilibria requires a correlated distributions, which you're postulating there must be some sort of common cause. Yeah. And then you gave several plausible common causes, and you asked us, in fact, maybe we could sort of suggest a few others. And so I wanted to do that. So self-similarity, you suggested genes, of course, but there's growing work on social networks that there's homophily. People tend to associate with others with similar perceptions, similar political views, and this is a very strong force that actually can give. I mean, it's now when one looks back at these correlations between smoking and obesity and so on, these weren't taken into account, and they're actually very strong effects, which could be naturally fitting into this framework, I would have thought. And another thing I wondered whether it could or could not give this precondition would be psychological biases. Humans are well known to have shared psychological biases. No one really knows why. I mean, we often try to find ways to get rid of these biases. But if we have a shared psychological bias in your framework, that would seem to potentially be advantageous. because it would create an asymmetry which would cause a correlation in the structure, and that's all that you seemingly need to then allow this to. Would that be plausible, you think?
Sure. The problem is that the self-similarity considerations, they have a very bad press with economists because they always say it's a sign of irrationality. So we may have psychological explanations for that, but we have to defer that topic to the psychologists. They should study that and the effects of that. And the descriptive theory of behavior, that is then useful and a useful thing to do, but that has nothing to do with rationality theory. That's what the economists say. So it's a fallacy. The self-similarity is a fallacy, they say, and which may have a psychological explanation, but no rationalization. And the point is that I wanted to give also. I would not like to simply to defer to psychology, even though it's absolutely useful and suggestive. But I would like to stick to the claim that it's also that I can rationalize these things.
Okay. So whether or not it's truly rational is another very interesting discussion. I mean, another thing that I wondered about is collective learning. So if you look at like reinforcement learning, these algorithms that we've taken from biological experiments or human experiments, it's with humans, pigeons, rats, they're all social. They're all social. So if you actually put these reinforcement learning paradigms into a collective behavior type situation, whereby what I learn kind of influences what you learn and vice versa, then it turns out not only does learning become much more effective, but individuals spontaneously learn the correlation structures in their environment without needing to know what those correlation structures actually are. So that, so if you're dealing with social agents that are learning together, then actually it might be inevitable that there's correlations in, some. So I was just thinking of that as potentially another. I mean, because one of the big questions is why do we see cooperation when we shouldn't see it, right? And you're arguing that it could be because of these correlation structures. And so I was thinking about these mechanisms.
I mean, I'm of course familiar with reinforcement learning, but that was always in the individual case, so that describes the individual learning processes. But I've never read anything about what you mentioned, the social reinforcement learning.
It's quite surprising it even works at all in the collective context, whereby the options you experience are not necessarily the ones you wanted to happen, because and not only does it work, but it's within 5% of provably optimal in any condition, because the economists using omniscience and so on can actually prove what the optimal strategies are, and then we can compare numerically what the learnt strategies are in the and learning individually and then pooling your knowledge together is terrible. Learning together allows you to get very accurate. And then the last question I had.
Mantas, did you know about that literature?
There's only one or two papers. Sure. And then the last question I had was about the last figure you had. If you could go back, because I couldn't see the axes, unfortunately.
Which one?
Just the last series of figures. If you just go back there, that's good enough. I can't see the axis there. I was just wondering what the axis was. The label.
That was the number of trials.
Yeah, so it's a very small number of.
And that was very fast because, but with the parameter adapting a little bit, that makes so that was always with the assumption of zero weight of initial weights, and then the convergence is very fast. But if the initial weight is much larger, then the learning
it takes
curves
longer
are
to
much
converge.
slower. But then you don't very well see the initial movements. That's then very tight, and you hardly see it anymore if we have here 100 trials. So I return to this one where it makes a surprising. So the joint defection goes up, and then it breaks down again.
But it's a small. I just wanted to make sure that that's the absolute number, because that's a very small number. Because I was wondering whether this required an assumption of sort of whether it would survive under the assumption of finite memory, and it seems it clearly would.
that comes about because the statistics has a large weight, and the prior and the initial weights are very low weight, and therefore the statistics has an immediate effect on the behavior. Yeah? Whereas we would expect a much lower learning from the statistics, and then you get a much smoother curve, which goes 100 tries or 500 tries or whatever. Yeah?
Cool. Thank
then
you.
It goes much lower, but that all depends on the numeric assumptions in the process. And you,
Thank you very much.
Okay, thank you. So you please send me the references. That's better
Okay,
now,
so in the classical prisoner's dilemma, you said there's no iterations, and the iterations is one way to make cooperation appear, and then your approach works with a common cause for both agents. And is it possible that somehow through these norms, that norms carry iteration in them, so that when you use norms to make a pattern appear, that sort of iterations enter through the back door, through the norms?
Also first of all, with the prisoner's dilemma, it's of course complicated. And so I gave the description of, as I always said, the single shot play. You play it once, and then we can look at finite iterations. We play together 100 times, and then of course we start cooperating, definitely. But the only Nash equilibrium is defecting all the time, all the 100 times, and the picture only changes if there's if the play is continued indefinitely or infinitely. And then suddenly the mathematics gets very complicated, but very different also. And people are excused that we are accustomed with approximating the finite case by the infinite case, which is kind of paradoxical. But in physics we do that all the time. I mean the point was that my point was that dependency equilibria may be suited to describe, so to speak, the normative state of a group of people. So the norms governing that group of people. And then the question is how that comes about. And then I'm also appealing to an iterated process. And so far we have appealed to these dynamic processes with these simple dynamics. Of course, one could imagine that if traditional games theory has theories about repeated play, so what are the dependency equilibria in repeated play, and may that be also an approach to. But there, I confess, I don't know. We simply haven't developed the mathematics of that, of repeated play in terms of dependency equilibria, because that gets very involved. It's complicated, but in a way, it's also it's not necessary, or not really. It's not really urgent, I think, because, as I said, a Nash equilibrium is not suited for describing the current state of a society or of a group. So somehow it's only the Nash equilibria in the infinite repeated play which may do so. But the dependency equilibria are well suited for that, or even in the single shot. So that's the momentary state of the group, the normative of the norms governing that group, and then we add an explanation how that may come about.
Thank you.
I've got two questions. One is in standard lab experiments with the prisoner's dilemma, you often see that there's a convergence to cooperate fairly quickly, like you have there. But then in the last round, people start to defect again because they see a chance of getting the bigger payoff. Did you simulate for that too? Did that work?
I know that, of course. You can turn that both ways. If it is announced that we play Prisoner's Dilemma 100 times, so it's fixed 100 times, then of course we, as I just said, we start cooperating, yeah, for a long time at least, and that's against equilibrium behavior in game theory. Yeah? As I said, the only equilibrium is continuous defection, yeah? And therefore, I mean, that's and then these findings are a criticism of game theory, yeah, somehow. So apparently, game theory is not empirically adequate. Now, but certainly, could we explain that that people start to defect at the end? I'm not sure. Perhaps not. Certainly it works only if it's announced that the end of the game is announced. If it goes on indefinitely, we won't observe that behavior. We would have to know, I mean, we know what the Nash equilibria are in the finitely repeated prisoner's dilemma, but I don't know what the dependency equilibria are in the finitely repeated prisoner's dilemma. Yeah? I simply don't know. Yeah? And as I said, that would be complicated mathematics, but it may be that is also then equilibrium behavior. Yeah? It would not be so surprising because there are really very many dependency equilibria. Yeah? It's a very large manifold. Yeah? So in a way, and that's of course a criticism. Yeah? So actually explaining behavior is still difficult with dependency equilibria simply because there are so many. Yeah? So why this specific equilibrium, not the other ones? So yeah, but there's still a lot of work to do. Yeah. Second question.
Never stops that work. The second question was, do you have yet any normative findings you would give to research communities that apply game theory, like, for example, in brackets, behavioral economists?
Yeah, sure. I mean, I think, of course, that the whole thing is relevant for behavioral economics, simply because, I mean, somehow the standard game theory is, so to speak, the normative benchmark for behavioral economics. And then the behavioral economists, they observe that normative benchmark is missed very often. Yeah? So that normative benchmark is not good enough to explain the actual behavior of people. Yeah? So we have to invent further things about the behavior of people, yeah? in the form of other regarding preferences, in the form of preference for fairness or whatever, yeah? And further considerations. Okay, but these considerations, of course, change from the beginning if the normative benchmark is a different one. Yeah? We haven't used the ultimatum game as an example because I think that's in a way boring for biologists because that's an unnatural game, but I guess for biologists, and it's also for humans, it's an unnatural game. Yeah? It's just a game invented for rejecting game theory. Okay, but in the ultimatum game, refusing your bad offer would be equilibrium behavior. Can be part of a dependency equilibrium. Yeah? So it's not just you leave me as little as possible and I take as little as I accept that. That would be the only Nash equilibrium in the ultimatum game. But rejecting then that bad offer from you would also be equilibrium behavior in the sense of dependency equilibria. So and that would change the presupposition of behavioral economics. That's one intention of the whole thing. And that's very, let's say, that's very common in all this cognitive stuff. In cognitive psychology, really a big thing is the so-called Wason selection task. And famous psychologists who really started that kind of enterprise then, and he's the godfather in cognitive psychology of a lot of investigations. His experiment was supposed to show that people make logical fallacies, and they do not only make correctly the modus ponens and the modus tollens and as inferences, but also such bad things like affirming the consequence. So if A, then B, one premise, B, therefore A. And everybody would say, well, that's a bad fallacy. But the people do that very commonly in that experiment, 70% of the people or whatever. So we are bad logicians, apparently. And then they have all kinds of additional explanations for that behavior. When you have a Bayesian theory of inference in terms of probability, then that inference is perfectly okay, and that behavior of the people is justifiable. So you change the normative benchmark, and then suddenly there's no need to call people irrational and to invent theories of irrationality. And cognitive psychology is full of such examples. But the race and selection task is about the most famous one. So changing the normative benchmark may have considerable repercussions.
One more. Go ahead.
So I was just thinking about what you were saying about rationality and the economists. I mean, we can argue about economists, being emperors with no clothes, to be honest. But if an irrational strategy can outcompete a rational strategy, would it not be selected for? I mean, why should rationality be held onto as this belief if it's not evolutionarily stable, for example, in the context of so-called irrational strategies?
When rationality is so defined to be successful, isn't it? If you maximize expected utility, so.
But there could be strategies, yes. So say you take that as your argument for rationality, that following the Nash equilibria, this is what you can prove that this strategy would. If that strategy were outcompeted by other strategies, would that cause you to question the whole concept of rationality?
At least to reconsider.
Or to reconsider it. Okay.
And that's the reason why in evolutionary biology they have refined the notion of a Nash equilibrium to that of an evolutionary stable equilibrium, which is not just a Nash equilibrium, but there's an additional condition to be satisfied, and precisely that Nash equilibrium solution cannot be invaded by other strategies. Is stable against such invasion. But we haven't thought about a corresponding amendment of the dependency equilibria or about the corresponding problem for dependency equilibria. We haven't thought about that so far. As I said, there's a terribly lot to develop with all these things. Of course, if you make a basic change at the very beginning of game theory, then you can start repeating all of game theoretical literature and trying to adapt that to that notion, and that's a huge work.
Well, it'll be good to chat about this at some point after.
But our intention is to do that, at least so far, that game theorists find that interesting. And then I would hope that if they find that interesting, then they would start working at that. That would be the hope. But I report in 5 years whether we succeeded.
Thanks again so much for the talk and also the vivid discussion and great questions. I assume it's perfectly all right to reach out to Wolfgang and Mantas in case of any further questions. So there's not much more to say than thanks them again and you for your attention, participation, and see you again next week. Thank you so much.
Thank you.